Hello. In this presentation, I will discuss the influence of strong magnetic fields on the properties of the hadrons using the non-Buchanan-Sinio model. The content of the talk is based on material that can be found in this publication. The reason for the interest on strong magnetic fields is that it has been argued that in some physical situations, like in the interior of compact stars or in the early stages of non-central heavy ion relativistic collisions, magnetic fields of the order of 10 to the 19 Gauss or even larger might exist. So in this work, I will concentrate mainly on the masses of the nucleons and of the ions. So I will start by showing you the Euclidean Lagrangian of the model I will use. So the first line here, you can see the kinetic term of the quarks coupled to the external electromagnetic field. Now here there is a scalar-scalar interaction and a pseudo-scalar interaction. These two are the ones that included in the conventional non-Buchanan-Sinio model. So in addition, I will consider a color gradient interaction, which will be necessary to address the diquarks and the baryon masses. So I will consider a constant, a uniform magnetic field that points along the positive third axis. So, and I will choose the Landau gauge. Since we're interested in hadron masses, I will bosonize the fermionic theory, introducing mesonic fields sigma and pi, and also diquark fields delta A. Once this is done, I will integrate out the fermionic fields, obtaining in that way a purely bosonic action. Next, I will expand such action in powers of the fluctuations around the mean field of the bosonic fields. I will assume, as usual, that only the sigma field has a non-vanishing mean field value. And the effective action looks something like this. This is a term which is of zeroth order in the fluctuation, which is the mean field contribution. Then there is the quadratic contribution, and so on. So at the mean field level, I have this action that looks very much like the one in the usual non-Buchanan-Sinio model without external fields, except for the fact that instead of having here the free propagator, I have the propagator in the presence of the external magnetic field. It was long ago by Schwinger that such a propagator can be written as the product of two pieces, one which can be expressed in terms of the so-called Schwinger phase, and which is not translational invariant, which you can see here, and another piece which is translational invariant, and therefore it can be Fourier transform. Here I am showing the explicit form of such Fourier transform using proper time. So one has this expression for the propagator, one can replace in the action and obtain some expression, which, however, is divergent. So one gets an integral which is divergent. So therefore, one has to regularize. And to do that, we will sum and subtract the B equals 0 contribution. In this way, one separates the B-dependent piece, which turns out to be finite, from the B equals 0 contribution, which is the one which is divergent. So we only have to regularize the second one, and we will do that introducing a three-dimensional cutoff lambda. This method is what is usually called magnetic field independent regularization method. So the quark mass M is obtained from the gap equation, which is obtained by deriving the mean field action with respect to the quark mass M. So at the quadratic level, one gets this action, which has a piece coming from the meson and a piece coming from the diquarks. Of course, those pieces are not diagonal in coordinate space. In fact, this inverse propagator here can be expressed as a sum of a piece which is diagonal and a piece which in principle it is not. So these functions here are the so-called Meson and Antiquar polarization functions. So I will show them in a minute for each particular case. So let's go to the case of the pi zero mass. In this case, the polarization function has this explicit form. As usual, it contains two quark propagators. However, in this case, both propagators correspond to the same flavor. Therefore, the Schwinger phase coming from one propagator cancels out the one coming from the second one. In this way, this polarization function is translational invariant, and thus it can be diagonalized by simply transforming the ionic field. Then one obtains this form for the quadratic contribution of the pi zero to the action, which of course is diagonal. And this polarization function in momentum space is, however, divergent. So its expression contains an integral which is divergent. So it has to be diagonalized. And as we did for the case of the mean field action, we will use the magnetic field regularization scheme, meaning that we sum and subtract the equal zero contribution, and then notice that the p-dependent piece is finite and doesn't need to be regularized. So, using the frame in which the pi zero is at rest, the mass of the pi zero can be obtained from this eigenvalue equation, where it enters regularized form of the polarization function. So let's go to the case of the pi plus pi minus. I will show it for the pi minus, but it's similar for the pi plus. So the polarization function of the pi minus is here, and you see now that here there is a D flavor, and here is a U flavor. So two propagators now correspond to different flavors, and therefore the corresponding Schwinger phases will not cancel. Therefore, the polarization function is not translational invariant, and it cannot be diagonalized using the Fourier basis. One has to find a more convenient basis. The one we used is the so-called Ritus basis, in which one expands the bosonic field, the pion field, in terms of these functions f, which might be called Ritus bosonic functions. And there are n waves in the 2, 3, and 4 components. However, x1 appears here through the row, the Hermite polynomial. This index k is a non-negative integer that levels the Landau levels. So it's an index that indicates the Landau level. Using such a basis, one obtains then a diagonal form for the quadratic piece coming from the pi minus. And here, this polarization function in Ritus space is again an integral which is divergent and has to be diagonalized, regularized, I'm sorry. And we did that using the magnetic field independent regularization scheme. Finally, the mass of the pi minus in its lowest energy state, meaning equal to 0 and Q3 equal to 0, is obtained from this eigenvalue equation. Once this eigenvalue equation is solved for the pi minus mass, one can obtain the energy of the lowest lying state from this equation here. So I have to stress that this expression is the same as the one corresponding to a point like Meson. The difference is that for a point like Meson, this mass is a constant, dependent of the magnetic field. So it's the mass for B equals 0, for example. However, in our case, this mass does depend on the magnetic field. And this is because we are taking into account the internal structure of the charge pion. So the mass of the diquarks. Now the polarization function has this form, and you see again that the flavors of the two propagators here are not the same. Therefore, the Schwinger phases will not cancel, and this polarization function is not translational invariant, so we have to use the Ritus basis in order to diagonalize it. So using that basis, we obtain a diagonal form for the polarization, which is an integral which is divergent and has to be regularized. And again, we use the magnetic field independent regularization scheme. So for the diquark mass in its lowest energy state, the mass can be obtained from this eigenvalue equation. And here, given the mass obtained from this equation, one can obtain the energy. And again, this equation is the same as the one for the point like quark. Difference is that for the point like quark, this mass is a constant, while in our case, it depends on the magnetic field. So for the calculation of the baryon masses, we will need the diquark propagator in coordinate space. And this propagator can be expressed as a product of the Schwinger phase and the Fourier transform of the translational invariant piece. So such a Fourier transform is given here, and it is expressed in turn as the sum over Landau levels of the diagonal polarization function of the diquark that we found before. Here, L is a Laguerre polynomial. So let's go to the case of the nucleons. As shown long ago, in the non-Boltzmann model, baryon fields satisfied a Faddeev equation. So this Faddeev equation is written here, and it corresponds to this diagram. So you see here we have the amplitude propagation of a quark and diquark corresponding to this part of the diagram, and the exchange of a quark, which corresponds to this part of the diagram. So now, in our calculation, we will use an approximation for simplicity, which corresponds to assume that the quark is exchanged here is very heavy. That we can use this approximation, so to replace the propagator by just 1/m. If we do that, we get this pair of equations, one for the proton and one for the neutron, where we have now to replace the propagator of the diquark and the quark we obtained before. So doing that, one obtains these equations, this for the proton and this for the neutron. And one has to observe here that in the case of the proton, there is a non-vanishing Schwinger phase, while in the case of the neutron, there is not. Therefore, to deal with the proton case, one has to use something like a Ritus transformation. While for the neutron, it is enough to use the usual Fourier transformation. The difference here is that this Ritus function here is the fermionic Ritus function that, as I'm showing here, can be expressed as a kind of combination of the bosonic ones and some Dirac operators. So in this basis, the equation for the proton and the neutron can be written in this way, where these for the proton and neutron are written here, and they are Dirac operators, which are combinations of the gamma matrices with some coefficients that depend on, that there are functions that depend on the quantum numbers of the particles. Of course, in our calculation, we obtain the explicit form of all these functions. Now, in order to obtain the mass of the proton and the neutron, we have to look for the place where the determinant of these operators vanish. And this leads to this pair of equations, which are written for the particular case in which the proton and the neutron are in their lowest energy states. So the lowest Landau level for the proton and at rest for the neutron. Here, these coefficients are integral over momenta and a sum over Landau level of the Dirac propagator in reduced space. So once I have shown you the formalism, I will now come to the numerical results. So in our numerical calculations, we choose values of the coupling constant T, lambda, and MC, reproduce the empirical values of F pi and M pi at zero magnetic field, together with the standard value for the quark mass of 350 MeV. So I'm showing in this panel the behavior of the ion masses as a function of the magnetic field. Here, this is correspond to the pi zero. So it's the ratio of the pi zero mass at zero magnetic field to the one at the final magnetic field. And as you see that we see there is a slight decrease with the magnetic field. However, our results are slightly above those of lattice QCD. On the other hand, for the charged pions, we obtain a strong increase of the energy as a function of the magnetic field, and such result is even larger than the one corresponding to a point-like ion. We see that our results are roughly consistent with the lattice QCD results, although they have large error bars. For the Dirac calculation, we have mass calculation, we have to fix the value of the coupling constant H. And what we'll do is to consider values of the ratio H over G, which are within those used in the literature. So I will consider 8.9 and 1. So here, this straight line here corresponds to the point-like diquark. So you see that our results are below those of the point-like diquark up to a certain magnetic field of around 0.4 keV squared. Above that value, our results are above those of the point-like diquark. So let's go to the case of the nucleus. So here I'm showing the case of the proton, and here the case of the neutron. You see that in the case of the proton, there is some dependence on the ratio of H over C. So, however, in all cases, we first find a decrease of the proton mass with a magnetic field up to a certain value, which ranges between 0.2 and 0.6, depending on the ratio H over C, and after which the proton mass starts to increase. We see that our results for low values of magnetic fields are consistent with those of chiral perturbation theory, while those of lattice QCD doesn't seem to be so. For the neutron case, we have plot here only the lambda -1 case, which is the one that has lowest energy. Now the dependence on H over G is somewhat smaller. Again, we observe first a decrease of the neutron mass up to a certain value of the magnetic field, and then an increase. We see here that the discrepancy with respect to the perturbation theory result is larger. We have a smaller slope at the origin, and this has to do with the fact that we underpredict the magnetic moment of the neutron. In fact, this is known in this kind of models. And the reason for that has been shown has to do with the absence of the diquark channel that we have not included in our calculation, and it will have to be included in a future one. So let me summarize the content of my talk. we have considered the masses of the pion, diquarks, and nucleons in the presence of strong magnetic fields in the context of the Nambu-Lensinian model. For the diagonalization of the charged pion and diquark polarization, we have used the reduced eigenfunction method that takes care of the Schwinger phases in a complete way. So we find that zero mass decreases slightly with the magnetic field, while the energy of the lowest lying charged pions display a strong increase with the magnetic field, and it's always above that of the point-like pion. For the diquark mass, we found that up to a certain value of around 0.4 CV square, our prediction is below that of the point-like diquark, while starting about 0.4 GB square, it is above such prediction. For the nucleons, we have considered Faddeev equation in the static approximation. For the one corresponding to the proton, we have used Riesz transform, while for the one corresponding to the neutron, we have used a Fourier transform in order to diagonalize the corresponding equation. We find that both the mass of the proton and the neutron first decrease with the magnetic field, and then starting some value in the range between 0.2 and 0.6 CV square, they both start to grow with the magnetic field. I will finish by just mentioning that we have also studied the leptonic decays of the charged pions, and the corresponding results can be found in this publication. So this is all I have to say. Thank you very much for your attention.